Engines. The Avro RJ is powered by 4 Allied Signal LF507-1F twin-spool high bypass ratio turbofan engines. Each of the engine's thrust is generated by a geared fan driven by the low-pressure spool. AC electrical generators are fitted to engines 1 and 4, hydraulic pumps fitted to engines 2 and 3. Fuel flow to each engine is controlled by a full authority digital engine control, FADEC, with mechanical reversion. An autothrottle system allows full thrust modulation by the flight guidance system. Each engine is protected against ice by the use of engine bleed air and internal hot oil spray. An overheat detection system provides fire warnings, and 2 fire extinguishers on each engine may be used to stop the spread of fire. The engine is comprised of the following 4 modules: a fan module, a gas producer module, a combustion turbine module, and an accessory gearbox module. The air passing through the fan is divided by a splitter. Most of the air is accelerated through the bypass duct, generating most of the engine's thrust. The remaining air is compressed by a 2-stage low-pressure compressor called a supercharger and delivered to the gas producer module. Here, air is further compressed to high pressure by a 7-stage axial compressor and a single-stage radial compressor before being delivered to the combustor turbine module. Fuel is delivered into the combustion chamber by multiple fuel nozzles. The fuel-air mixture is ignited and exits via a 2-stage high-pressure turbine, which drives the high-pressure compressor stages. Before exiting to atmosphere via the jet pipe, the hot gases are passed through a 2-stage low-pressure turbine, which drives the 2-stage supercharger and a fan via a reduction gearbox. Each engine is fitted with an accessory gearbox which is driven by the high-pressure shaft. The systems driven from the accessory gearbox differ depending on the position of the engine. Each accessory gearbox drives a fuel boost pump, a hydromechanical unit, HMU, and an oil pump. In addition, it drives a hydraulic pump on the inboard engines or an AC generator on the outboard engines. For engine start, a starter motor is fitted to each accessory gearbox. A drain mast is fitted to the bottom of each engine cowling and contains sealed drain lines for the system shown here. Bleed air is extracted from 3 different points on the engine for air conditioning and ice protection. The upper bleed port is used for air conditioning, airframe ice protection, and other air supplies. The other bleed ports are used for engine ice protection. Engine anti-ice. The fan spinner is continuously anti-iced by an internal oil spray. The air intake lip and the airflow splitter are separately anti-iced by hot bleed air taken from the final stages of compression. Hot air can be bled via 2 engine anti-ice valves on each engine, controlled by a single switch on the ice protection panel. The valves are pneumatically actuated and electrically powered shut. Selection of engine anti-ice illuminates engine anti-ice on the central status panel. When the airflow splitter anti-ice valve is open, engine valve not shut illuminates on the ice protection panel. This indicates that hot air is being delivered to the splitter. Operation of the air intake lip anti-ice valve is indicated by 2 annunciators on the ice protection panel. Intake low pressure indicates low pressure beyond the intake anti-ice valve and should extinguish when the engine is operating above flight idle. Intake high pressure indicates that the intake anti-ice valve has failed to regulate the bleed air pressure correctly. Either caution is accompanied by ice protection on the central warning panel. To prevent engine surge, the engine anti-ice valves are automatically opened during engine start. To prevent high EGT after start or cutout, engine anti-ice is selected on before start. Bleed band. In order to allow correct response of the engine during starting and periods of acceleration or deceleration, air is bled from the high-pressure compressor by opening and closing of a bleed band assembly, controlled from the FADEC. Fuel system. Fuel is delivered by the AC boost pump in the wing feed tank via a low-pressure shutoff valve, which is controlled by the fire handle to the engine-driven low-pressure fuel pump. It then passes through a fuel heater to a low-pressure filter. Should the filter become blocked, filter clogged will appear on the central warning panel. Fuel then passes through the hydromechanical unit, HMU, which contains a high-pressure pump, a high-pressure shutoff valve, and a metering valve which under normal operations is controlled by FADEC. The high-pressure shutoff valve allows the engine to be stopped and is directly controlled by the thrust lever. From the hydromechanical unit, fuel is fed to the fuel nozzles in the combustion chamber. Ignition. During engine start, ignition is provided by either ignition system A, B, or both. Ignition is automatically terminated when combustion becomes self-sustaining. The ignition system is not normally used after engine starting, but continuous ignition A or B must be selected on when operating from contaminated runways and when flying through areas of severe turbulence or heavy precipitation. Engine ignition is also used during in-flight engine start. This is covered in the engine starting module. Oil system. The oil system is completely self-contained and includes an oil tank, oil pump, oil fuel heat exchanger, and an oil filter for each engine. Oil is replenished at the oil tank, which contains a dipstick and a transmitter for the oil contents gauge on a flight deck triple gauge. The oil pump, which is located on the accessory gearbox, also contains the oil filter. Low oil pressure is indicated by oil low pressure on the central warning panel. Each engine is divided into two zones for fire detection purposes. The area between the fan casing and the cowling is termed Zone 1. The area between the engine core and the core casing is termed Zone 2. Each zone is equipped with two fire loops, designated Loop A and Loop B. Each pair of loops is connected together in parallel to form two independent detection systems. Either pair of loops may be selected as the active detection system on the engine fire detect panel. Failure of a loop will illuminate loop fault for the appropriate engine on the central warning panel. When an overheat condition is detected by the selected loop, the warnings shown here are given. The fire bell and the red alert flashers may be canceled by pressing either of the red alert flashers. All the other warnings will cancel once the temperature at the sensor falls below a preset limit. The fire warning system for each engine may be tested by the use of 4 engine fire test buttons on the ground test panel. Pressing an engine fire test button activates all fire warnings for that engine, plus the appropriate loop fault warning and both amber attention getters. When an engine fire is detected, it is important to isolate all surfaces on that engine which may support combustion. This is done by 4 fire handles, one for each engine on the overhead panel. Each fire handle requires 3 distinct actions to be pulled to its full extent. Pulling to the first bulk illuminates engine fire handle on the central warning panel. This indication is provided to confirm that the correct fire handle has been operated. Twisting the handle to pull it through the bulk and pulling it to its full extent achieves the actions listed here. A fire extinguishing system is fitted in Zone 1. A fire in Zone 2 may only be extinguished by shutting the engine down. Two fire extinguishers are fitted in the nose cowl of each engine and are electrically activated to operate independently by turning each fire handle either anti-clockwise, shot 1, or clockwise, shot 2, after the handle has been pulled to its full extent. Confirmation that a fire extinguisher has been signaled to operate is given by either extinguisher number 1 used or extinguisher number 2 used, illuminating on the overhead panel for the appropriate engine. These extinguisher used indications may be tested by pressing the engine and APU extinguisher test button on the ground test panel. APU extinguisher used also illuminates on the APU panel. Do it, please. To protect against extinguishant thermal expansion, each fire bottle is provided with a pressure relief valve and indicator on the inboard and outboard side of each nose cowl. These indicate red if a fire bottle has discharged due to thermal expansion. Two fire access and pressure relief doors are also fitted on each engine. Engine vibration level, fan speed N1, exhaust gas temperature EGT, gas generator speed N2, fuel flow, fuel used, and fuel contents are indicated by the primary engine display PED. Oil contents, temperature, and pressure are indicated on 4 separate so-called triple gauges. Engine vibration. This is indicated in inches per second. An indication exceeding 1.2 inches per second for more than 2 seconds will activate the engine vibration warning on the central warning panel. Operation of the vibration test button on the center panel causes the vibration level to increase to 2.0.
Do it, please.
N1 set. Target N1, as computed by the flight guidance system, is displayed in the N1 set window and as an amber command bug on the N1 gauge. Following the failure of the RPF, Arctic fail appears in the N1 set window. N1 can be manually set by pulling the pull set N1 knobs at the bottom of the PED and rotating them to the required value. When target N1 is set manually, a letter M appears in the N1 set windows as a reminder to the pilot. The meanings of the color codings on the N1, N2, and EGT gauges are shown here. N1. N1 is indicated as a percentage of maximum fan speed. The maximum operating limit, which is both the takeoff and the maximum continuous limit, is 97%. Actual N1 is indicated by a pointer. When actual N1 matches commanded N1, the pointer lies within the command bug. A transient overshoot of 100% is permitted for a maximum of 10 seconds. EGT. Gas temperature measured in a jet pipe is indicated in degrees Celsius. The normal operating range extends to 613 degrees Celsius, defined as maximum continuous thrust, MCT. The takeoff range extends to 632 degrees Celsius and is indicated by the red radial. The maximum operating limit of 649 degrees Celsius is defined as the EGT limit during engine start and wind shear recovery.
The maximum transit overshoot of 713 degrees Celsius is permitted during engine start only for a maximum of 15 seconds.
N2. N2 is indicated as a percentage of the maximum core speed. The maximum normal operating limit is 96.9%. The yellow arc or maximum takeoff limit extends to 98.8%. As for N1, a transient overshoot of 100% is permitted for a maximum of 10 seconds. Maximum operating limits. When a maximum operating limit of N1, N2, or EGT is exceeded, the leading block illuminates. If the leading block contains a digit, it appears in inverse video. If the exceedance lasts for more than 10 seconds, the whole numeric display will flash. Fuel used and fuel flow. When no fuel flow is present, the display shows kilograms or pounds dependent on the aircraft configuration. After engine start, fuel flow is indicated. When the push Fuel Used button is pressed, the display shows fuel used.
Do it, please.
But reverts to fuel flow 10 seconds after the button is released. The fuel used counters may be zeroed with the reset button, but will automatically revert to zero after about 20 minutes without electrical power.
Do it, please.
Triple gauges. A triple gauge for each engine provides indication of oil quantity, pressure, and temperature. Thrust is set by reference to fan speed N1, which is measured as a percentage. 100% corresponds to 7,600 RPM. At sea level, at 23.3 degrees Celsius with a standard pressure setting 95.1%, N1 will give the rated thrust of 7,000 pounds. Below this temperature at 95.1%, N1 thrust will increase above rated thrust. To prevent engine damage, thrust is limited to 7,000 pounds below 23.3 degrees Celsius by limiting N1. This is known as flat rating. Above 23.3 degrees Celsius, thrust falls as the density of the air decreases and the takeoff EGT limit of 632 degrees Celsius is maintained. This is known as full rating. Fan overspeed protection. If N1 exceeds 104%, the engine will automatically shut down and the caption "Engine Overspeed" will light on the central warning panel. An engine overspeed test button is provided on the ground test panel, which multiplies actual N1 by 4 and feeds the signal to the overspeed controller on the appropriate engine. The thrust control system is comprised of the thrust levers, full authority digital engine control, FADEC, the thrust rating panel, TRP, the auto throttle. Thrust levers. Each engine is controlled by an individual thrust lever. It is fitted with a bulk to prevent inadvertent closure of the high-pressure fuel valve when the engine is at idle. A trigger mechanism fitted to each thrust lever allows the bulk to be passed and the fuel valve to be closed. Between fuel off and idle is an immediate fuel on position, which is used during a FADEC off start. thrust lever is mechanically linked by cables to the HMU. Numbers 1 and 4 thrust levers have an auto throttle disconnect button on each outer side. Numbers 2 and 3 thrust levers have a toga button on their front face. This button signals the flight guidance system to engage the takeoff or go-around modes. A fire warning light is fitted in each thrust lever. FADEC. The FADEC system consists of a hydro-mechanical unit and electrical control unit on each engine and provides the functions listed here. During FADEC manual reversion, the fuel metering valve within the HMU is mechanically controlled. Under FADEC control, the mechanical link is broken and the thrust lever angle is electrically transmitted to the ECU, which then electrically controls the metering valve within the HMU. FADEC trim control of N1 is between 5% at high thrust settings and 18% at low thrust settings. The FADEC status panel above the PED contains the FADEC trim arrows and the FADEC fault indicators for each engine. The fault annunciator illuminates to indicate a FADEC failure. FADEC will also illuminate on the central warning panel. FADEC is selected off by pressing the fault annunciator. Following a FADEC failure or manual reversion at high thrust levels, the engine thrust is frozen until the lever is retarded to region. Thrust rating panel. The TRP provides an interface between the pilot and the thrust control system. It allows the selection and display of any thrust rating as calculated by the flight guidance system and the setting and display of the EFIS speed reference bugs. In order to extend engine life, a takeoff thrust below maximum rated thrust can be used. This is done by basing the takeoff thrust calculations on an assumed temperature which is higher than ambient, which produces a lower thrust. This is called a flexible thrust technique. When the aircraft is on the ground, the TRP is selected by pressing the toga button. In flight, pressing any of the buttons on the front of the TRP will select it on. Selection of TRP modes provides appropriate M1 targets to FADEC and for display on the flight deck. Click on the TRP thrust mode buttons to view information about each mode. Each thrust rating is continuously calculated for pressure, altitude, temperature, and bleed selection, and is displayed on the PED and in the TRP window when the rotary selector is set to N1. By moving the rotary selector to temp with Toga Max as the selected thrust rating, the sensed outside air temperature is displayed in the window when the rotary control is turned clockwise by one click. A correction to OAT may be made using the rotary control. The flight guidance system uses the lowest of the set and sensed temperature in its calculation of N1 ref. With Toga reduced selected on the TRP, the temperature displayed will be T reduced, a standard increase over OAT.
Do it, please.
N1 reduced is now displayed on the PED. T reduced may be manually amended to any temperature above OAT to produce T flex and a related N1 flex. Due to manufacturing differences, each engine produces a different thrust for a given N1. To ensure that rated thrust is not exceeded at the maximum indicated N1, an electrical bias is applied to the N1 signal by FADEC to make all four engines appear to be at the same N1 without exceeding maximum rated thrust. When equal thrust is required, compensation is applied to the N1 signals to the primary engine display and the flight guidance system. This occurs when either Toga or MCT are selected on the TRP. Equal thrust is then achieved by each engine at apparent equal N1s. With climb norm or climb max selected on a TRP, the compensation is removed to synchronize the engine's true N1s and so reduce cabin noise. The TRP rotary selector is also used to enter the bug reference speeds V1, V cross, and V dot on the EFIS speed tape. When V1 is selected on the TRP, a bug is placed against the speed tape and the V1 speed is repeated at the bottom of the speed tape. The V1 speed and bug disappear when the aircraft is in flight. The TRP is selected off by pressing either the auto throttle disconnect buttons on the end of the thrust levers 1 and 4 for longer than 3 seconds. Auto throttle, the link between the flight guidance system and the auto throttle servo motor adjacent to the thrust levers, allows full authority thrust control by the flight guidance system. The auto throttle is selected on arm using the switch on the mode control panel. This can only be done if the TRP is on. Indication of autothrottle engagement is given by the green light adjacent to the switch on the MCP, and AT in white meaning armed, or green meaning active on the PFD. The autothrottle is disengaged by using either of the autothrottle disconnect buttons on the thrust levers 1 and 4, or by deselecting the autothrottle arm switch on the MCP. When the autothrottle is manually disengaged, AT on the flight annunciator illuminates for 4 seconds, and AT on the EFIS flashes for 4 seconds. An automatic autothrottle disengagement is indicated by the same warnings, but they will remain on until canceled by pressing either autothrottle disconnect button on the thrust levers. The thrust control system has the here listed modes of operation. Manual reversion. This is the most basic form of thrust control, which is made by movement of mechanically linked to a fuel valve within the HMU of each engine. No engine parameter limitation protection is available apart from fan overspeed protection at 104% N1. N2 ground idle will be between 49 and 75%. In flight, the pilot must ensure that minimum N2 is manually set. Thrust automatics off. The FADEC is selected on. The thrust lever's control of the fuel metering valve in the HMU is disconnected, and the electronic control unit now controls the metering valve electrically. The introduction of FADEC allows greater engine control and performs engine limitation protection and N2 idle control. N1 is limited to 97%, N2 is limited to 98.8%, and EGT is limited to 649 degrees Celsius. Ground idle is controlled to 50% N2, but depending on environmental conditions, it may be between 49 and 54%. To guarantee engine acceleration, minimum flight idle is 60% N2. To ensure that sufficient air is still available to provide air conditioning when bleed demands are placed on the engine, a minimum N2 must be determined for all bleed conditions at all altitudes. This is known as the N2 floor schedule and is automatically provided by FADEC. The minimum N2 in flight with engine NTI selected on is 67%, but reduces to 60% below 200 feet radio altitude. Thrust modulation. Selecting the TRP on raises the thrust control system to the thrust modulation level and provides a link between the flight guidance system and FADEC. The FADEC now has a limited control authority as demanded by the flight guidance system and provides limitations protection for N1, EGT, and N2 in all modes with the following exceptions. When wind shear is detected, 649 degrees Celsius EGT is allowed rather than the normal takeoff limit of 632 degrees Celsius. Independent of which thrust rating is selected on the TRP, with the auto throttle off, 632 degrees Celsius becomes the FADEC limit. The pilot is responsible for preventing the engines from exceeding the maximum continuous thrust limit of 613 degrees Celsius in MCT or climb thrust ratings. Basic mode. This mode is entered when climb norm or climb max is selected on the TRP. All the N1s are synchronized to the N1 of the master engine, as selected by the master switch on the TRP. If any thrust lever is moved away from the master engine, FADEC will eventually reach the limit of its trim authority and the pilot must advance or retard the thrust lever as indicated by the arrow on the FADEC status panel. A blue arrow indicates the thrust lever should be advanced, and a white arrow it should be retarded. The arrow will extinguish when FADEC authority is regained. Thrust mode. The thrust mode is entered from the basic mode by either selecting level change, climb on the MCP, or selecting any thrust mode on the TRP. When the thrust mode is entered, FADEC will control N1 within its control authority. The blue arrows will again appear when the limit of control authority is reached. The current thrust mode will be displayed in the top left-hand corner of the PFDs. White when the mode is armed and green when it is engaged. The calculated N1 is shown on the N1 set displays on the PEDs, along with the bug settings on the N1 gauges. The following thrust modes are available. Auto throttle. In auto throttle mode, the flight guidance system controls N1 to a thrust schedule by moving the thrust levers using the servo motor instead of commanding the pilots with trim arrows. The auto throttle may be overridden at any time by manually advancing or retarding the thrust levers. Auto throttle speed mode. In the auto throttle speed mode, the auto throttle controls N1 to maintain either Mach or indicators as selected on the MCP. Retard mode is entered after either a selection of level change, during descent, or automatically when radio altitude is below 50 feet.
Do it, please.
Auto throttle thrust mode. The thrust mode is engaged on takeoff, during a go-around, and during a climb, with either takeoff or IAS engaged as the autopilot vertical mode. Engine life computer. The engine life computer records certain engine parameters both routinely and when engine limitations are exceeded. Engine parameters may also be stored by use of the Store Data switch. The fail annunciator illuminates either when the unit fails a built-in test or when the memory is greater than 80% full. Click yourself through the external checks. After the battery or batteries have been selected on, the engine fire test must be performed for all 4 engines. Starting with the number 1 engine, when the fire test button on the ground test panel is pressed and held, the following indications should appear. One of the red attention getters should be pressed to cancel the fire bell and the red alert and caution lights. The engine extinguisher used indications are now tested by pressing and holding the engine and APU extinguisher button on the ground test panel. The 8 engine extinguisher used captions illuminate while the test button is pressed. Note that this test also illuminates the APU extinguisher used caption on the APU panel.
Do it, please.
The 4 fire handles are checked fully in. The center panel is now checked. Each indicator of the oil triple gauges is checked for condition and the contents checked. The FADEC fault and off annunciator should not be illuminated if all the FADECs are functioning normally. The engine vibration system is checked by pressing and holding the vibration test button on the center panel. The engine vibration indicators increase to 2.0 and engine vibration illuminates 2 seconds after the reading has risen above 1.2. When the button is released, the vibration level reduces to 0.
Do it, please.
The N1 settings, both N1 ref and N1 reduced, dependent on the pressure altitude, temperature, cabin air bleed, and engine anti-ice condition, are calculated before takeoff. With the rotary knob on the TRP selected to temp and a toga button selected to max, rotating the rotary controller by 1 click will display the sensed outside air temperature in the window. If this is different from the reported outside temperature, the reported temperature is entered in the window. The flight guidance system uses the lower of the 2 temperatures to calculate N1 ref. The calculated values are then checked against the values calculated by the TRP with the intended bleed selection for takeoff selected. The following configurations are permitted for takeoff: no bleeds, APU air selected on and packs on. Maximum thrust is available from the engines. Cabin air on, engine air selected on and packs on. Discrete signals from any engine air switch and either pack switch combine to signal this configuration to the TRP. Engine anti-ice on, engine anti-ice selected on and the engine air off. A discrete signal from any engine anti-ice switch signals this configuration to the TRP. When this configuration is used, air conditioning is normally provided by the APU. The selection of APU air by itself does not affect the TRP calculated N1. It is not permitted to select engine air bleeds and engine anti-ice simultaneously for takeoff. If an invalid bleed selection is made with a takeoff setting on the TRP, the N1 set numbers on the PED will flash. If a reduced thrust takeoff is performed, N1 ref is normally manually set in the N1 set window on the number 1 engine for reference. N1 reduced appears in the other N1 set windows. The intended thrust rating for takeoff, either toga max or toga reduced, is set on the TRP. Note that the rating appears on the top left of the PFD. Reduced thrust must not be used for takeoff with flap 33 or if the runway is contaminated with standing water, snow, slush, or ice. During ground maneuvering and wind speeds greater than 15 knots, do not exceed 55% N1 except for takeoff. The engine anti-ice must be on during all ground and flight operations. When icing conditions exist, are anticipated, or if the ice-detected caption is illuminated. Immediately before takeoff, the auto throttle may be armed by selecting the auto throttle switch to AT arm. The green light adjacent to the switch illuminates and AT appears next to the selected thrust mode on the PFD. For takeoff, the thrust lever should be advanced to 45% N1 and either toga button pressed. The auto throttle mode displayed on the PFD will turn green and the thrust levers will advance to the target N1. If achieved N1 is more than 1% below target N1, the takeoff should be abandoned. When the wind speed is greater than 25 knots from a direction of 55 degrees or more off the runway heading, do not use toga reduced. Perform a rolling takeoff and set takeoff thrust when aircraft ground speed equals wind speed. Takeoff performance is scheduled on the basis that the thrust levers are not moved during the first and second segments of the takeoff. At 80 knots, the thrust level calculated by the FADEC is frozen, and the auto throttle is clamped until 350 feet when FADEC unfreezes and the auto throttle enters the inactive armed mode. The auto throttle remains in the armed state until a new thrust mode is selected by the pilot or is automatically entered by the flight guidance system. Following an engine failure below 350 feet, if full thrust is required during a reduced thrust takeoff, a toga button must be pressed and the thrust levers manually advanced to the bugged value. After flap retraction, thrust rating is set to climb norm by either pushing thrust on the MCP or selecting climb norm on the TRP. N1 is now continually calculated for altitude and temperature by the flight guidance system. Climb norm normally remains selected on the TRP for the remainder of the flight. After the flight guidance system has captured the selected altitude, the auto throttle now enters speed mode and thrust automatically reduces to maintain the selected IAS or Mach. Descent may be made in either level change or vertical speed modes. Selecting level change places the auto throttle in retard mode. The thrust levers retard for 12 seconds before the auto throttle enters the arm mode. In this mode, full manual control of the thrust levers is available. Selecting vertical speed places the auto throttle in IAS or Mach mode. IAS or Mach, as selected on VCell, will be maintained by the auto throttle. Vertical speed is the aircraft attitude through the flight director and autopilot. During an ILS approach, when the autopilot is in glide slope mode, the auto throttle enters speed mode and controls the speed of that selected in the VCell window. At 50 feet radio altitude, the auto throttle enters retard mode irrespective of autopilot engagement. The auto throttle should be disconnected on touchdown before IAS is less than 60 knots. If a go-around is initiated, the mode automatically reverts to GA max. This can be reduced to GA reduced by pressing toga on the TRP. After checking the APU generator output, engines 1 and 4 may be shut down during taxi. As a maintenance check, the pilot is required to test the fan overspeed shutdown system on each engine every day. The N1 of all engines should be increased to 30%. The engine overspeed button on the ground test panel for the engine to be shut down first is pressed.
Do it, please.
After N1 begins to decay, the thrust lever should be moved to the fuel off position. Engine overspeed illuminates on the central warning panel. This indication should be cancelled by selecting Flight Start to On and Start Select to Engine 4. The remaining engines may then be shut down using the appropriate engine overspeed buttons. Start Select is rotated to the relevant engine after each shutdown to cancel the central warning panel warning. With the TRP selected, the interface between the FADEC and the flight guidance system is broken. The following functions are now not available. N1 ref and N1 reduced must be calculated using the tables provided in the checklist. It must be noted that the N1 values presented in the tables of N1 for takeoff and go-around take into consideration N1 compensation. Therefore, with compensation not available, 1% must be subtracted from the values derived from these tables before they are entered into the PED. After takeoff, N1 should be manually set for the appropriate altitude and temperature as given in the tables and the MOM. Every 5,000 feet, the thrust lever should be advanced to the tabulated value. The pilot must monitor the EGT to prevent exceeding 613 degrees Celsius. FADEC off. In order to protect against surge, the engine anti-ice of the affected engine must be selected on for the entire flight. If performance is limiting, the engine anti-ice of the affected engine only should be selected on. Performance data must be extracted from the appropriate tables or graphs at OAT plus 4 degrees Celsius. If takeoff performance is not limiting with engine anti-ice on, all engine anti-ice should be selected on. If a single engine anti-ice is selected on, a discrete signal is sent to the TRP, which now assumes all engine anti-ice is selected on and calculates N1 accordingly. In this case, the TRP must be selected off by pressing either auto-throttle disconnect button for more than 3 seconds. N1 for engine anti-ice off should be calculated and manually set in the N1 set windows of the 3 unaffected engines. N1 for engine anti-ice on is set in the window of the affected engine. If the TRP is used during climb, climb norm may be selected. The N1 of the affected engine should be matched with those of the other 3 engines. During the descent, the N2 of the affected engine must be matched with those of the other 3 engines.
In addition to engine anti-ice of the affected engine being on at all times, the following is mandatory to improve surge margins.
The auto throttle must not be used with any FADEC selected off.
In-flight failure of FADEC is indicated by a fault on the FADEC mode panel above the relevant engine. FADEC also illuminates on the central warning panel. Let's have a look at the abnormal and emergency checklist. The abnormal and emergency checklist FADEC fault shows the two failure indications for verification. Let's go through the procedure.
This procedure tells us when at a safe height to disengage the auto throttle, turn on the relevant engine anti-ice, and if above 31,000 feet, to turn on the outer wing and tail anti-ice. It then tells us to retard the relevant thrust lever until control of the engine is acquired. Do not reduce below and annunciator switch to off. Should the relevant pack be inoperative, outer wing and tail anti-ice must be on above 15,000 feet. Note the FADEC inoperative information below. This completes the A&E checklist FADEC fault. Following severe damage to an engine, it must be assumed that fire is present. The engine fire caption of the relevant engine may or may not be lit depending on the failure. If the red engine fire caption is lit, the fireball should be canceled. The correct memory item should now be executed. The A&E checklist engine fire, separation, or severe damage consists of memory items only, which the crew must know by heart. The relevant thrust lever is confirmed by both pilots, then moved to idle, and then to fuel off. This closes the engine high-pressure fuel valve and prevents fuel from reaching the engine. The relevant fire handle is pulled to the first detent. This action is confirmed by engine fire handle illuminating above the red warnings on the central warning panel. After confirmation, the relevant fire handle should be twisted through the detent and pulled to its full extent. The fire handle is now rotated to extinguisher 1. Should the engine extinguisher number 1 used annunciator not be lit, the handle must be rotated to extinguisher 2. If the fire caption is still lit after 30 seconds or there are other signs of fire, the relevant fire handle must be rotated fully to extinguisher 2. As with any fire on board an aircraft, timing is critical and the aircraft must be landed as soon as possible. On ground, if the fire is confirmed, an evacuation must be initiated. If time permits, the engine shutdown subsequent action should be accomplished. Let's have a look. The A&E checklist engine shutdown subsequent actions tells us to switch off the relevant engine air and engine anti-ice. This extinguishes the NIPS indications. An engine failure reduces the performance capabilities of the Avro RJ. Therefore, the TCAS should be selected to TA only. If an outboard engine has been shut down, the relevant generator should be selected to off, reset. Within its limits, the use of APU should be considered. If an inboard engine has been shut down, the relevant engine pump should be switched on to confirm on. Use the fuel balancing procedure or the two engines inoperative procedure if required. This completes the A&E checklist engine shutdown subsequent actions. Warning of low pressure is given by an oil low pressure annunciator central warning panel. The A&E checklist engine oil low shows the red oil low pressure annunciation for verification and tells us to check the relevant oil pressure indicator on the triple gauge. If the pressure indicator is in the red sector or below 50 psi to above 80%, the engine should be shut down. If the oil pressure is above 50 psi or above the red sector within less than 80%, the engine may be left running while monitoring its parameters and oil pressure. An engine vibration value in excess of 1.2 will illuminate engine vibration on the central warning panel. The engine which generated the warning must be identified by looking at the PED. The abnormal and emergency checklist tells us to turn off the auto throttle and TRP and check for any confirmatory signs of engine malfunction. If engine malfunction is not evident and the vibration level of the relevant engine does not vary within 1, an indication fault can be suspected, and the engine may be left running while monitoring its performance. If vibration does change within 1 and the vibration level can be kept below 1.2 units, the engine may be left running while monitoring its performance. However, should an engine malfunction be confirmed, or if the vibration level cannot be kept below 1.2 units, the engine must be shut down. Click on the different parts of the table to see related notes. Congratulations! You have now completed this module.